All right, we'll go ahead and get started. Welcome to Algorithm Design for Web Developers. Just a quick warning that the code examples are in TypeScript, but I'm hoping that we're all somewhat at least familiar with JavaScript, so that won't be too much of a problem. So thank you for being here at IPC, and if you're visiting from Manali, awesome. Happy to have you. And my name is Michael Dowden. I have spoken at a number of conferences, including in this very room. So really excited to be back here. I spend a lot of time building web applications and web-based products. So that's kind of where I spend a lot of my time. I have my own consulting business, headquartered in the US, but living here in Germany. So I am a huge fan of games, board games in particular. This is just a sample from my collection. I have somewhere on the order of 300 different board games and expansions. And I'm going to use board games initially to help illustrate algorithms, at least a little bit. So we have two board games here, Settlers of Catan and Monopoly. Has anybody played either of these games? Yes. What do they have in common? They share one core mechanic.
2d6.
Two six-sided dice. That is correct. So at the start of every turn, the active player rolls two dice. And we total them and figure out what happens. Exactly right. So whenever you roll two six-sided dice, I'm not telling you anything you don't already know, you get a number between 2 and 12. And when we roll them a lot, we expect to see a certain distribution of results that looks something like this. It's a normal curve. There's only one way to make a 2. There's one way to make a 12. There's 2 ways to make an 11. As it shows right there. There's 6 different ways to make a 7, which means that a 7 is the most likely outcome, right? And so this seems really simple, but the cool thing about algorithms is the only thing that's different between evaluating a really simple algorithm like rolling 2d6 and a really complex algorithm is how many steps we have to go through. The principles of how we evaluate the algorithms remains the same. And so this is a simple example that it's really easy to walk through. Anytime I'm looking at permutations or combinations of possible results through an algorithm, it might be very helpful for me to understand the likelihood of any given outcome or the different pathways through a system, for example. And sometimes I need to do that by actually running simulations. So here is a code-based setup. We have a simple random int method that's going to return a number between a low number and a high number, in our case, between 1 and 6. To roll 2 six-sided dice, we're going to call it twice, and we're going to add the numbers together. Right? So I'm going to say random, give me a number between 1 and 6, add it with another random number between 1 and 6. No big deal. And then I'm going to do that 10,000 times. So that, and push those results into an array so that I have something to evaluate. We can then calculate our results and show them against the expected values to verify or approach rolling dice. I don't like running code live for various reasons. I ran the code, you can trust me, I promise, and I put the results underneath the chart there. Now, it's never going to be exactly right, no matter how many times you do it. The expected number and the actual number, there's always going to be some differentiation there, but it's pretty close. 273 is almost 277. 287 is almost 277, right? You can see by looking at this that it's very close to what we expect. And that's a way of evaluating an algorithm. We ran it through a simulation, we look at the results, and we see if it matches up with our expectations. If there's a significant difference between what we actually see in the simulation and what we expected, then we may have a bug, we may have an issue, or we may have a flawed expectation of how the algorithm actually performs. So, how we produce those statistics, the way we calculate those numbers is what's really interesting. That's the algorithm I want to look at right now. One method we can use is a brute force method. We can iterate over every single possible value of the 2 dice, and for each value we're looking for, we can look through the entire array of results. And in this case, I'm pushing the results into an array to display them all at once. I could have output the results as I went, but I'm doing this in order to calculate for each possible value from 2 to 12 how many times that value occurred. Can someone point out to me a possible problem with this approach? N square. Correct. Basically, I'm going through the loop twice. I am doing a lot of work. Because anytime you see nested iterations, you have a potential problem with your algorithm, unless you really, really, really understand the algorithm well. There's other methods we can use. One really straightforward thing we can do is what I'm calling the array count. It builds an array with indexes from 2 to 12, and then quickly calculates against that. Now, I'm only iterating once. We would expect this to be a lot faster. There's another thing built into JavaScript, and that's the reduce method. In this case, I'm going to use reduce to accumulate results. And what's interesting here is I didn't pre-create an array. I'm just kind of creating the array of results on the fly based upon what showed up in the actual data, which is interesting. Now, how are we going to choose between these different approaches? What's the best approach? So one thing we can look at is algorithmic complexity. We can look at the number of operations, the performance, maybe the elapsed time, how long did it take us, the memory requirements. And in a minute, I'm going to talk about how to collect various metrics in order to perform the evaluation. Right now, I want to look at how do I look at the results of those evaluations to determine which one of these is better. So at a quick glance, which of these algorithms do you want to use? Which one?
Array count.
You want to use array count. Why?
It has the lowest operations, elapsed time is tied for last memory.
Basically, it's the fastest and the cheapest. That is a reasonable assertion. So the operations that we were counting here are both the comparison and assignment operations. So the first little asterisk there is assignment and comparison operations are not created equal. One of those is slower than the other. The other is that the elapsed time is, if you look at this, you'll notice that the elapsed time is lower. It's not necessarily proportional to the number of operations. Brute force is actually doing more operations per second than the other two are, interestingly enough. And the reason you start seeing things like this is that compilers are very good at optimizing. So even when we write really stupid code, sometimes it performs better than it should because the platform that we're running it on is smarter than we are. It happens all the time. In fact, I dare say there's a lot of software in this world that exists only because really smart people worked around the really dumb ways we write software sometimes, and that's fine. The memory used here is nominal, but I always include some sort of memory count in algorithmic evaluation. And the reason is there are a large number of algorithms that trade memory consumption for CPU cycles. And there's lots of ways we can trade off between those two things. So it is really important that we look at both of those. But there's a couple other things I want to point out, and that is that there's more to the story than just that. There are also qualitative things. Reduce required no setup. I didn't have to know in advance how large the possible result set was. I happen to know that it's a value between 2 and 12, but maybe I decided to roll, 4d6 or 5 six-sided dice instead of just 2. That drastically changes the result set. That reduce code would have run perfectly with no alterations. The others, I would have had to go in and change the code. There's no mutability at all in the code that I wrote for reduce. Every other algorithm that I created leverages mutability in some way. And it's not entirely accurate. It's using mutability, but it's constrained within the actual function, right? It's closure scope. So it's very, very safe. And like we said, no knowledge of the data points. So there's sometimes advantages, and I'm going to try to convince you that reduce is the best option. But the other thing we can look at when we're looking at different algorithms is the cyclomatic complexity. And at a high level, this is just a measure of the number of unique paths through a function. So multiple ways of exiting from a function increases the cyclomatic complexity. And it's usually a symptom of a couple different things. One of them is that maybe the function could be further reduced into smaller, simpler functions that are easier to test and easier to verify the performance characteristics of. This is a report on the code that I wrote for this talk specifically. Don't try to calculate this yourself. There's lots of third-party tools that you can use for doing this. This was Codalyze. So I am not a performance expert, and this is not a performance talk, but improved performance is a possible side effect of good algorithm design. It is not necessarily the primary goal. Okay? There are lots of other reasons we might choose an algorithm besides the fact that it is the fastest. That said, we do expect all of our algorithms to be reasonably efficient and at least to perform within expected tolerances. We want to have some idea of how fast or slow it's going to be. And as web developers, this generally means that we don't want the users to have to wait. We want to provide a good experience. And there's a lot of techniques that we can use to provide a good experience that don't necessarily mean improving the algorithm under the covers. So when we're assessing an algorithm, we need to see clearly defined inputs and outputs, and we expect it to be robust. This means that it produces correct and consistent results. An algorithm that does not give us predictable results is often not super useful to us. This is a topic of conversation that comes up a lot these days as we leverage AI for more and more things in software development, right? There are lots of operations inside of our shipped applications that we should not use agents for example, because it's possible they could produce unreliable results. In some places, when we're dealing with people, that's fine. We can there's an error rate that we can accept. In financial applications, in medical applications, the error rate we can accept is usually 0. So that's important. And finally, we want our algorithms to be clear, meaning that they are easy for developers to understand and that they are obviously applicable to the situation to which they are applied, and therefore easy to troubleshoot, but also easy to maintain over time. Now, some of these goals have clear, measurable metrics. Others are a little bit more subjective. And hopefully, this helps indicate why I might prefer one algorithm versus another. So I'm always going to use array.reduce as opposed to doing multiple iterators unless I have a compelling reason that I must choose the fastest possible algorithm. It's almost never the fastest. It is almost always the one that requires the least maintenance and the one that is easiest to read. So to do the algorithm analysis that I just showed you with not just rolling the dice, but more importantly, counting up the statistics on what it took to roll the dice and to measure the results, I had to gather a number of metrics. So the first thing that I had to do is calculate the amount of memory consumed by the application. Within JavaScript, this is a pretty good framework for doing that. This URL, this gist, provides the code you need to actually calculate. It's not 100% accurate, but it's a very good approximation of memory consumption inside of a JavaScript application. And there may be a couple surprises in here. The array is calculated based upon the size of the thing stored in the array. That makes sense. If I've got an array of size 10, it's going to be 10 times whatever's inside the array, which is great so long as you only have one type of data inside of the array. If you have lots of different types of data inside the array, now it becomes a little bit more complicated. A Boolean, you might expect to be 1 bit. It is not. It is, in fact, 4 bytes. That's one surprise we might run into. Using Booleans can chew up memory faster than you would expect, etc. Strings are 2 bytes because they're UTF-16. And there's a lot of things that in order to approximate the size, you convert them to a string and calculate accordingly, which is weird, but it's strangely effective. Again, approximation. The other thing we want to do is measure time. And the first biggest mistake that I see is use of date.now in JavaScript to measure time in an algorithm. And this doesn't work for a really big reason. It's not precise and it's not reliable. This 2 calls to date.now, time could actually go backwards. And I've actually seen this, especially if you're console logging this. There's no guarantee that every single time you call date.now, that time progresses forwards. There's no standard for precision. It is an approximation of the current time every time you call it. So you can use console timers. They can be used for quick and dirty measurements. They're fairly useful. They go straight to the console. So if the only thing that you need to do is a quick evaluation, you can look in the developer console, see how long something took, this is great. There's a couple small tricks. That unique name does in fact have to be unique, which means if you're measuring the performance of a lot of different things, you have to come up with a lot of different unique names, or a strategy for keeping those names unique, or you're going to run into timer collisions. Note that you're going to have that problem with basically every timing technique that exists. It's fairly limited that just goes to the console. The better option is probably to leverage the performance API. This was specifically designed as a precise measurement for gathering performance metrics. If you need high performance timestamps that actually guarantee that every call is at least the same value as the previous call and maybe higher, you can use performance.now. It does exactly what you would expect date.now to do, except that it actually works. And it is more granular. I believe it may be microseconds, and to some extent the accuracy is going to be based upon the platform that you're on. You can also use the mark and measure methods. Mark basically says, I want to start measuring, and then at measure it says, okay, now tell me how long it took. And you can call measure multiple times, and it's going to give you the new updated delta from the original mark every single time you call it, which is kind of cool. The really cool thing about this is that actually goes directly into the browser's performance statistics. So if you go to the Performance tab in Google Chrome, for example, all of those markers are going to show up in the timeline of events that happened with your application, which means that now you can see the real-world evaluation of performance of your algorithms alongside other things the browser is doing. So that is super useful. The other thing that we need to be able to do is quantify the operations being performed. There's a couple different ways to do that. One is to just look and count, right? I can kind of glance at this and have a pretty good idea that that first loop is going to be looping 11 times. That next one is going to be looping 10,000 times. And then I can count how many operations there are, multiply by those numbers, and I can figure out that we're going to have about 220,000 comparisons. That's only because this is a really simple algorithm, right? The other thing we can do is actually just count. We can add counters into the code and then run it. That's going to give us a much more accurate count of how many times this happened. And yes, I routinely find errors in my calculations when I do this. Gee, I forgot that was actually running one more time than I thought. So this is a pain, though. We don't want to do this a lot. You want to do this when you really, really, really care about how many calculations or if it's really hard. There's a lot of algorithms that are not really predictable. We don't necessarily know how many times certain parts of the code are going to be executed because it's totally dependent upon the structure of the data that comes in. So in that case, I want to implement counters like this within my algorithm, and I want to run it against real-world data sets to get real-world analysis. An example of this would be basic sorting algorithms. Different sorting algorithms have different performance characteristics, different speed at which they will execute based upon the data that comes in. If the data that you're trying to sort is typically totally random, then some sorting algorithms work better. If the data you're trying to sort is typically already sorted, then a completely different set of algorithms may be faster. And that's why actually measuring the real-world scenario with the actual data you plan on running through your algorithm can be very valuable. So one of the really important evaluations of algorithmic complexity takes the data that we've collected and applies to that the asymptotic notation. The asymptotic notation is an approximation of relative complexity of different types of algorithms. So the three basic notations are this. We have big omega, which represents the asymptotic lower bounds. This is the best case scenario. In other words, this is the fastest this algorithm can ever complete. It is the fewest number of operations that can ever be used, etc. You have big theta, which represents the case where the running time is the same in all cases. In other words, there's no difference between the best case scenario and the worst case scenario. There are algorithms like this. They are not all like this. Then you have the big O notation, which is the most common one used in computer science, and this represents the worst case running time. Typically, what we really care about is what's the worst case? What is the worst that could happen to me? I find that it can be quite useful to know best and worst case, because then I understand the total delta, what's the range of possible outputs that I'm working with. Or I want to run this on real data. So what we're going to look at is when you graph these different possible outputs, you see very clearly the difference in relative complexity. Order 1 basically means it doesn't matter how much data I throw at it, the algorithm's going to use the same amount of time to complete, for example. It's static time, static operations. Order n means that you change exactly proportional to the number of inputs. So if I'm iterating 1,000 times versus 10,000 times, there's only a 10x difference between how much memory I use or how much CPU I use, for example. Log n escalates slightly slower than that, n squared much faster than that, and then, heaven forbid, you have exponentially increasing something like 2 to the n. Those are very bad. Don't do those. But I say that, and the thing is, there's an exception to everything. It doesn't matter if you have an algorithm that has an exponential cost if you know it's never going to be more than 10 items. Who cares? It doesn't matter. But if I don't know, then I care, or if I know that I'm dealing with really, really large data sets. So part of our goal in evaluating an algorithm is to apply the real-world constraints to the work we need to get done. So small data sets or simple but large data sets may open up a whole set of algorithms that I couldn't use if I don't know what data is going to get thrown at it in advance. So the better I know and understand the scope of the data that I'm using, the more options I may have available to me. And one of the mistakes that we sometimes make when developing systems is to assume that we're ignorant about the problem domain. But we're often not. So we end up building systems that can handle anything, even though they're never going to be expected to do so, and we may be actually penalizing our users in terms of performance or in terms of some of the features we could provide by pretending that we don't know things about the data that we actually do. In order to map out, I'm going to look at specifically the big O notation for your application. You want to start calculating the operations performed for different data sets and then graph them on an XY plot. It's going to look something like this in our case. And you're going to find, and like I talked about before, you're going to find that elapsed time doesn't scale proportional to the number of operations because, again, compilers, platforms, CPUs have built-in optimizations. But the memory used stays the same because the total possible number of produced values didn't change in this particular algorithm. Memory used, this is how we plot it. Memory used is just order 1. It didn't change. I mean, technically, it changed in the smallest because if you do a small enough number, I didn't actually end up with every single possible result of 2 dice, so I used slightly less memory on the first one. Operations versus n. Very straight line. Perfect. It's order n. Elapsed time. Still, effectively, if this will move forward. Okay, we're going to do the keyboard, I guess. Still order n. So one of the things that comes up in talking about algorithms is one of the largest anti-patterns in software development called not invented here. How many times have you been asked to solve a problem, and so you start thinking about, if I write this code and I do this thing, I can solve this problem, and it's going to be really cool, and then you share it with the rest of your colleagues, and they're like, well, why didn't you just use this library over here that does it faster, better, cheaper? It already existed, right? And it's important to consider that as an option. When we're busy, it's really easy for us to just keep our head down and continue doing the same thing we're already doing. If we're writing code to solve problems, we're going to continue throwing code at problems, maybe without stopping and taking a step back and thinking, hey, is there something else out here? So, for example, you need to calculate a time zone. What are you going to do? Oh, that's easy. I need today's date a year ago. I just subtract 365 days. I have today's date a year ago and keep going. Who thinks that's going to work? Right. You have leap years every 4th year, except non-leap centuries. Now you've got to subtract those back out. What about leap seconds, right? You don't do these things by yourself. You use libraries to do them. We all know that. This is an obvious example. I think we all know that that's a bad idea. But when you end up with specialized algorithms, you may not realize that what you're doing is much harder than it looked like on the surface. On the surface, it looks like a date a year ago is subtracting 365 days. It seems obvious. That happens to us all the time in real-world data processing. Another one, geographic distance. How do you calculate the geographic distance between 2 points? It's just the Pythagorean theorem, right? Except for a little problem. The Earth is round. For very small areas, this is very close. It's a great approximation. It's quick and dirty. This is where we get into how precise do we need to be in our algorithms. There's levels of precision. This is an approximation algorithm for distance. If you need it over a larger area or there's a lot of topography, maybe it's a really hilly or mountainous area, that doesn't work as well. You need something more like the Haversine formula, which exists specifically to solve this problem. If you are asked for the very first time to solve a geospatial problem and you've never heard of the Haversine formula, you don't know that that's a solved problem potentially. And this is where we have to kind of be inquisitive and ask, this feels like a problem other people would have run into. I wonder what the name is for the thing we're trying to do. This exists in every single imaginable area. Different sorting algorithms, insertion sort, selection sort, quick sort, merge sort. Which one is better depends upon our data. Does anybody know which sorting algorithm JavaScript uses under the covers if you just do array.sort? Quicksort? Anybody else? What? No idea? The answer is, usually it's quicksort, but JavaScript actually evaluates the type of data inside of your arrays, and I think it even keeps track of if it suspects the array is already sorted or not, and chooses an algorithm based upon your data. It does not guarantee that it's always going to run quicksort. And in fact, you don't want it to, because quicksort is not always the fastest. It's the best general case sort, but it's not the best in all cases. So it tries to outsmart you and figure out what you're doing and what's maybe the most applicable thing here. Different types of searching. When you're searching for data structures, and part of it depends upon what is the structure of your data. I have a whole other talk that I do on data structures specifically, because there's a huge interaction between the data structures we use to represent our information and the types of operations we can perform upon that. So one of the things that's super compelling to us when we're thinking about how to solve technically challenging problems in building algorithms is, can I make this algorithm simpler or cheaper by simply changing the structure of the data that it's stored in? Different data structures can give us better results. Data compression, Huffman coding deflate. So these are just examples of well-known within computer science algorithms that have existed and been tested for a very long time. Are they always going to be the fastest or the best? Not necessarily, but it's a really good default starting point. You do not want to write your own search algorithm unless you know why you're doing it. For example, when we're on the web, there's a lot of other considerations that we may have about the algorithms we choose. This one, who's run into this one? We send the requests faster than we get responses. We don't want to do that. Has anybody here ever DDoS'd your own server from the front end? Yes, thank you, my people, okay. But it happens. Like, these are things we have to be careful about. Are we tolerant of high latency? Ever been on a cruise ship? Dealt with cruise ship Wi-Fi? It's terrible, especially when you are south of Chile. It's very bad, very, very slow. Don't recommend. How much data do we use in our application? But just as importantly, how much data are we actually moving around? Are we passing the right amount of data? One of the times I gave this presentation, somebody talked to me and basically mentioned that they were working on an application that was sending n-squared data when they only really needed to be sending order n amounts of data. They were just sending more data than they needed to. They could have connected the dots on the client side instead of sending all that information from the server to the client. That chewed up a lot of API time. When we're wanting to perform a search, do we search in the client? Do we pass all the data to the client, let the client do the search? Or is it better to do lots of back and forth? To some extent, that depends on the amount of data it is. It depends on how many times the search is being performed, how quickly we want to get the results, how do we apply filters. I always prefer to sort small data sets on the client if I could get away with that from a security standpoint. Sometimes we can't. If we're dealing with large data sets, we have to send the searches to the server, but then we may need to debounce. We need to maybe wait until the user has typed a certain number of characters. We've got to be careful about character thresholds, though, because the number of times I have seen name-based searches that required you to type at least 3 characters, which is a really big problem if your last name is only 2 characters. I mean, I have seen this many times. It's an easy problem, but it's easy to overlook. We can do pagination on the client if the data set makes sense, but if we're paginating on the client, then we need to search in the client. If we're paginating on the server, we need to search in the server. This is another mistake I've made where you do the searching on the server and then the pagination on the client, and the results seem to bounce all over the place from the user perspective. There's a limit to the number of DOM elements you can have on a page inside the browser. Anybody ever blown through that stack? Yeah, you're generally recommended to keep it under 800. That's where Lighthouse starts yelling at you. Basically, 1,400 is your practical upper limit. Most machines stop working at about 3,000. And that's a problem. And what's interesting is the number of times I have had to write my own UI libraries, not because I wanted to, not because it wasn't already a solved problem, not because I had anything to offer it whatsoever, other than that the algorithm that they used or the way they chose to present the information sucked. It didn't account for large amounts of information. It worked great for displaying 10 images on the page, but when I had 10,000 images I need to display, suddenly, oh no, there's a number of DOM elements we can't display. So you've got to get creative sometimes. You've got to think about things like rendering and painting. How quickly am I turning around and changing things? How often am I painting? When do I cause page performance issues based upon the way I'm doing algorithm updates? Do I want to break up an algorithm so that I can show incremental step results as I'm doing a calculation or I'm working through a problem to show the user progress and give them periodic updates? Or do I want to just do the work, let them wait, and then give them a result? And sometimes it depends on how long we expect it to take, and sometimes it depends on what the user's expectations are, right? Sometimes it's totally fine. If we're not blocking the user, if we can go behind the scenes and do stuff and maybe give the user some additional information or maybe give them a form and say, hey, give me these additional details that I also need later. They're sitting there typing, and by the time they're done, the work is done. I've used that in a few different cases. I've got one app that I built where we've got to do this whole heavy round trip to an AI server to fetch information about an image that they've uploaded. And it takes a long time, quite frankly. It's a number of seconds. It would be painfully slow for them to sit and wait, so I don't. I have them filling out the next section of information. I've never had a user notice that it took time because I was keeping them busy while I was doing the work behind the scenes. So sometimes we don't fix the algorithm, we don't fix the API, we just fix the user experience. So when we're talking about algorithms in particular, there's some vocabulary that it's really important to know and understand, and run through these really quickly. Atomic is a single operation is required. This doesn't mean a batch. Batch is different. But an atomic operation means I do one thing and maybe change the state of operations. For example, I do a lot of hosting on Firebase Cloud Hosting. A Firebase Cloud Hosting deploy is an atomic operation. It obviously takes time to move all the files up and to prepare the server, but all that happens behind the scenes. Changing from the old version of a website to a new version of a website is just moving a pointer on the network. Boop, and then I moved over to the new thing. There's all kinds of things we can do by prepping in advance and then doing a single atomic update from the user perspective. Idempotent, multiple calls, same result. This also means stable. Orthogonal, I can change the implementation of one part of the system without impacting other things. Composable means that I can assemble in various different arrangements without side effects. The side effect is an unintended or unexpected change that happens as a result of intended operations. I have this thing that I want to do, and this other thing happens that I didn't expect. Mutability or immutability. Mutability is the ability to modify. Immutability means that I cannot modify. Immutability is safer from an algorithmic standpoint because I can't accidentally change the underlying data set. This is very hard to accomplish in JavaScript because JavaScript is naturally mutable. Deterministic means that no randomness is involved in whatsoever. It means every single time I give this specific input, I get the exact same output. And finally, pure functions, which involves deterministic idempotent functions with no side effects. And pure functions are a glorious way to do really composable systems and build algorithms that can grow in a very orthogonal way. So when we are evaluating algorithms, it's important to weigh a variety of criteria and look at how they fit into our overall software solution. Of course, the performance, but what is our performance with real-world data sets? What is our worst case cost, the order n squared, et cetera? Are we tracking the correct metrics? Am I looking at the right operations? Am I measuring time accurately? Am I actually certain about the memory consumption involved? Do I have a memory leak somewhere that I'm not freeing up? So maybe I've got a really efficient use of memory, but I never actually free it up. So once you've done 5 or 10 operations in a row, now I'm using a lot more memory than I should be. Does my code support idempotency? Is it orthogonal? Do my algorithms work for a wide range of data inputs so that I am not constantly changing the code as the data or my expectations change? And then finally, consider the more subjective measurements. Is our code easy to understand? Are we using commonly available libraries to solve problems? Are we using published solutions with community input, or are we writing our own solutions from scratch without looking at the other options that are out there? And of course, how hard is it going to be to maintain our solutions over time? So that is a summary, high-level 101 of algorithm design. Hopefully you've gotten a little something out of this. Hopefully you have a great time at the conference. I know I have so far today. Don't forget to vote and leave feedback for all the presenters, including myself, throughout the event. I'm going to hang out for a little bit, but I think we've got another session coming up soon. So thank you very much.